Hi guys, welcome back to my channel. So we're going to be looking at some complex familiar examples of solving or integrating trigonometric functions, and we're going to do that using our trig identities. And in the previous video we looked at trig identities that had even powers. So for example, if I had cos to the power of 2 or if I had sine to the power of 4, and we could use one of those trig identities, substitute those values in, and then simplify and solve. So with this, we're going to do a similar process, except we might use a little bit of a different trig identity, and this is just going to sort of depend on what the question is asking. Now, I will actually tell you, I did go through and I did attempt to use this identity, because this identity was one that we used previously. But when we do that, keeping in mind that we're going to have this angle in here, a to the power of x, and then this angle is now going to become 2 lots of that. And that worked in our previous example when we were just adding and subtracting things. But now what we're going to do, we're going to first factorize out the sine squared, and I'm going to pop this 3 out the front at the same time to give me, voila, this function here. And I know the temptation is there to just do that and to just substitute that in, because that's the first thing that I did. But what that actually does is that changes this angle in here, doesn't it? Because that will double the size of that angle when you replace it with this. And then what we would have to do is we would then have to multiply this by sine again. And we can't really multiply cos of x by sine of x over 2. It's not going to work. But what will work if I do 2 of the same angle? So if I was to do cos x times by sine x, then I could actually use another one of my trig identities. So I don't want to mess with this angle inside the bracket this time. Okay, so that's why I've chosen to use a slightly different trig identity to solve this particular problem. And I'm using this simple trig identity here. Cos squared ax plus sine squared ax is equal to 1. And I've just rearranged that, so now I have sine squared ax is equal to 1 minus cos squared ax. So that's a little tip for you. If you've tried to integrate by substituting in sine squared ax is equal to a half 1 minus cos 2ax, and you kind of got a little bit stuck, try integrating using a different trigonometric ratio, because different things will need different, processes, and see if that works instead. Okay, so let's keep going and let's substitute that value in here now. So I've got 3 lots of the integral 1 minus cos squared, not ax, x over 2, because we do have a value for that. And that's going to be multiplied by sine x over 2 dx. This is starting to look a little crazy, and I think that you may notice that, look, we've got cos squared again, and so would we have to substitute in maybe the other trigonometric identity, cos squared ax is equal to 1 half 1 plus cos 2ax, or would we have to substitute in this in a rearranged form? What would we do? I'm actually not going to do any of that, because I think if we continue to substitute in those trig identities, it's going to become more and more complex, and my goal here is really to simplify. So to do that, what I'm actually going to do is I'm going to let cos x over 2 equal to u. And then I can find the derivative of that function. So du dx is going to be equal to, when we find the derivative of cos goes to negative sine x over 2. And then when we are deriving, we are going to multiply by the derivative of the inside function according to the chain rule. So timesing by half, same as dividing by 2. Okay, so now what I want to do is I want to rearrange this so that I have this expressed in terms of dx. So now I can substitute back into my original equation. And so that's going to be pretty simple, because 2 du over negative sine x over 2 will be equal to dx. And now I can substitute that in. So let's rewrite this using our u's and our du's. Now we've done this, I think that the next step should be to simplify as much as we can. And we can do that. This is just going to end up cancelling each other out. I don't like using that word cancelled. I think that they're dividing into each other, and when they divide into each other, they get a value of 1. So it's not cancelling. I don't like to say that, but I think that's the simplest word that I can use to describe what's happening here. And now let's simplify this again. So we've got 3 lots of 1 minus u squared multiplied by negative 2 du. And again, I'll just pop this negative value out the front here. So I've got negative 6 lots of the integral of 1 minus u squared du. And this is now going to be a nice, simple function that we can integrate. So we're going to have negative 6 lots, and since we're differentiating with respect to u here, negative 6 lots of u minus u to the power of 3 over 3 plus c. So let's substitute those values, or that expression for u, back into the equation, and then I'll show you the final result. Oh, and again, I forgot to put the plus c. My own name starts with c. I don't know why I forget that c every single time. Okay, and I've just gone into the back of your textbooks as well just to check that, and that is the correct solution. Your textbook has this written as the other way around, so 2 cos cubed x over 2 minus 6 cos x over 2 plus c, but the values are going to be equivalent. All right, so let's jump in and let's do another complex familiar example using odd powers of sine or cos. So let's look at this example from your textbook. So this is on page 351, question 11a. And again, we can see that we've got this odd power for sine. So we're going to use that rule that we derived from before. So sine squared ax is going to be equal to 1 minus cos squared ax. So that's just come from that Pythagorean identity, is where this formula is derived. And the other thing that I'm going to do is I'm going to pop this 4 out the front. I'll rewrite this as sine squared times by sine, and then I'll come back. So I've just underlined using this green color, so hopefully you can see where I've substituted in. So the next thing I'm going to do now is expand these brackets. So I'm going to multiply cos squared x over 3 sine x over 3 by this 1 minus cos squared x over 3. And I forgot to close that little bracket, so let's do that now. So I've just applied that across the brackets, and then I've factorized out that sine. Okay, so the next thing I'm going to do is something similar to what I've done in the previous example. And what I'm going to do is I'm going to let u equal to cos x over 3. So now I can go ahead and replace this with u squared, and I can go ahead and replace this with u to the power of 4. Once I've done that, the other thing I need to replace will be this dx. So again, I might use some different colors to just show you where I've substituted these particular values from. Okay, so substituted those values in, and again, I've just used those colors to help you, to show you where I've done that. And this is going to make this nice and simple now, because this 1/3 I can take out the front of the integral sign because it's a scalar value. These two terms are going to divide into each other to be equal to 1, and then I'm just going to be left with some u's, and I'm going to have to integrate the u's with respect to u, and so that's going to be something that I am able to do, because we do not have any more of those x variables present. So let's finish this off now. So I've just replaced those, and I've written it a little bit neater. So like I said, we're just going to integrate now with respect to u, and so that's going to give me 4/3 u to the power of 3 over 3 minus u to the power of 5 over 5 plus c. Let's distribute this 4/3 across the bracket. So I'm going to get 4u to the power of 3 over 9 minus 4u to the power of 5 over 15. Excuse me. And then last thing, let's substitute that u back in. And remember, u was equal to cos x over 3. So we can write this, I might write this up here. So that's going to be equal to 4 lots of I don't need to put the bracket there, that was a bit silly. 4 lots of cos x over 3 over 9 minus 4 lots of cos x over 3 over 15 plus c. Now I've just gone back in the book and I've checked the answer, and I've actually got this answer wrong. And what I've realized is I've done this bit here wrong. I've been doing integrals and derivatives all day. So this should actually be over 3 here, because we are finding the derivative. So we are multiplying by the derivative of the inside function, not dividing by the inside of the derivative function. I do apologize. Let me go through and fix those values. So luckily that was an easy fix because I've divided by 3. So then that's just going to flip when I have flipped that equation. And so this should be 4 times 3. So I should be multiplying by 12, not by 4/3. So luckily that was an easy fix for me there at the end. All right, so that is an example of a more complex solution. And again, it never seems to be the hard stuff, the complex stuff that we stuff up on, because as soon as as soon as you understand the process, you just go through and you just work through the process. The problem is those silly little algebraic errors, and it happens all the time, just simple little things. It's like in my previous one where I was doing 1 over 24 times by 1/4 is 1 over 48. It's just those silly little mistakes that we just have to be a bit aware of. So keep that in mind. It's okay to stuff up. If you've realized you've stuffed up, go back. If you stuff up in an exam, I can see that you've got most of that procedure right, and that's what I'm looking for. You would have only lost maybe a half a mark or 1 mark if you had made that same mistake that I had made for a complex familiar example, because you can show me that you understand the process. All right. So I'm going to have a go. I don't know if I want to do a complex familiar example for this one because, it's a pretty similar process again. I might have a look at exercise 6.5 next, integration of inverse trig functions, and I'll see you in the next video. Bye guys.